This second video for chapter 2 is all about chemical bonds. So bonds are going to be what hold atoms together and allow us to create molecules. Okay? Now, there's a lot of information on these slides, and there's a lot of slides over bonds, which tells you that they're important. But you guys know how to read, so we're going to focus more on what I'm going to expect you to be able to do on the exam and to understand for the exam. So with electrons, on the last video I told you that we are unable to pinpoint exactly where an electron is. Okay, and that's true. But what we are able to do is figure out how close are they to the nucleus and what general vicinity are they going to be in. And that's because electrons belong to certain shells. Shells is the term that I'm going to use and that you're going to see on your exam. So this is just going to be the nucleus, okay? And so then the electrons file out into these shells. I'm sorry, I'm not a good artist. You're going to realize that really quick. So whenever we have an atomic number, so let's pretend that our atomic number is 6. Remember that tells us that we have 6 protons, but because we're dealing with chemically neutral molecules, if we have 6 protons, we're also going to have 6 electrons. So we know that there's 6 electrons somewhere around this nucleus. So where are they? Well, closest to the nucleus is shell number 1, and this one can only hold 2 electrons. That's it. Okay, so we know that 2 of the 6 are in this vicinity closest to the nucleus. Outside of that is the next shell, and this one can hold up to 8 electrons. Okay? But hopefully you're thinking, well, Chelsea, you just drew 8, but our atom that we're talking about only has 6 electrons. So that's true. So if 2 of those 6 are in the first electron shell, how many should be in this second shell? Just 4. Okay? So this is what we call an electron distribution diagram. Okay? I suggest that you write in your notes, electron distribution diagram, and then you get ready to sketch this next example, because I do expect you to be able to do this for the exam. So we are going to do oxygen. So oxygen is abbreviated with an O. It has an atomic number of 8 and an atomic mass of 16. So what would its electron distribution diagram look like? Okay, well, we go to the atomic number here. It shows that we have 8 protons, so we know we're also going to have 8 electrons. So here's my nucleus. In our first shell, we're going to put 2 of those 8, and that leaves us with 6. I'm really horrible at drawing, sorry. Especially in this weird camera setup I have going on in my office. So we have 1, 2, 3, 4, 5, 6, 7, 8. Voila. Well, you might be saying, well, what about atoms that have more than 8, or even perhaps more than 10 electrons? Where do theirs go? Well, that's a really good question. And so for atoms that have more than 10 electrons, they have a third shell, okay? And so this third shell, so let me get rid of this so I don't confuse you guys. So here's shell number 1, maximum of 2. Shell number 2, maximum of 8. Shell number 3 also has a maximum of 8. Okay, and that's as far as I'm going to ask you guys to go in this class, okay? So we're going to be looking at those atoms that have no more than 18 electrons, okay? So as you can see on this slide right here, this is an atom that has 15 protons. That's what these numbers mean. P stands for protons. Okay, so phosphorus has 15. So it has 2 electrons in the first shell, 8 in the second shell, and that's going to give us 10. So that means it's going to have 5 more. 1, 2, 3, 4, 5. So here's where I need you to understand this picture, because this is all in your book, and I think it can be a little confusing. So the purple circles are actual electrons, okay? And so that's why you see 1, 2, 3, 4, 5 purple circles in this outermost shell, because it needed 5 to reach the total number of 15. So what are these white things? Well, remember that this third shell can hold up to 8 electrons, and so they're representing that 3 more could go in this shell. Okay, but it only has 5 because there's 5 purple ones. So these white circles are vacancies, so to speak. Okay. Now, an atom is happiest when all of the outermost shell is full. Okay. So for instance, 8 here, this is oxygen, okay, which we drew a second ago. Oxygen has 8 protons. So it fills up the first shell, and it has 6 electrons in the outermost shell. But in order to be really happy, it needs 2 more, okay? Because this outermost shell, we call the outermost shell the valence shell, it likes to be full, because that means it has everything it wants, and it's stable, it's good to go, okay? Atoms that don't have their valence shells full, they're going to want to form bonds, because remember, bonds deal with electrons. So by forming a bond with some other molecule, it's going to be able to fill these vacancies, because again, it wants this outermost valence shell to be full. So hydrogen here has only 1 valence shell, okay, because it's only has 1 proton, so it's only got 1 little shell. Carbon, nitrogen, and oxygen all have 2 shells, so the valence shell is the second shell, whereas phosphorus needs 3 shells, so its valence shell is shell number 3. We call the electrons in this valence shell the valence electrons. All right, so let's talk about bonds real quick. So again, an atom wants to have its valence shell full. So here we're looking at carbon. Okay, it's got 6 protons, so 2 in the first shell, and it's remaining 4 in this second shell. But remember that that second shell can hold up to 8. So it only has 4, so it needs 4 more. So what happens is it can form 4 bonds with hydrogen, because look at each individual hydrogen. It's got 1 proton, but how many does the first shell hold? 2. So hydrogen needs 1 more to be happy. So what you're going to see happening if you look at this right-hand picture, by sharing electrons, all atoms are going to be happy. Okay, so here's 1 hydrogen. So it's giving its 1 electron, and it's sharing with 1 of carbon's electrons. And that's happening here, and here, and here. So now notice, hydrogen wants 2 electrons in its valence shell, so it's got 1, 2. It's happy. This hydrogen has 1, 2. It's happy. This hydrogen has 1, 2. It's happy. This hydrogen has 1, 2. It's happy. So all 4 of our hydrogens are good. What about our carbon? It had 6 protons to begin with, but each hydrogen donated or is sharing 1 of its hydrogens. So we have 1, 2, 3, 4, 5, 6, 7, 8. So carbon's valence shell is full and everyone is happy. Okay, so again, look at this middle portion where hydrogen is. It had 1 proton, it needed another one. So it just goes over here and it links up with carbon and says, hey, you need 1 and I need 1, so let's share. So each hydrogen is going to be sharing an electron with carbon. We call these covalent bonds, okay? Covalent bonds are sharing a pair of electrons. A pair is 2, so that means carbon was donating 1, hydrogen was donating 1. So they were sharing a pair of electrons, okay? All right, but it turns out that how these electrons get shared isn't quite as straightforward as you would think. So imagine that you have a sibling and you both want the same toy, right? Rarely do kids just harmoniously play with the same toy. They share it for exactly the equal amount of time, right? That doesn't happen. Somebody always wants that toy a little bit more and is going to kind of hoard that toy more than the other kid. And so the fancy term for being greedy or hoarding electrons is called electronegativity, okay? So the more electronegative an atom is, the more greedy it is. Kind of think of it as the more electronegative and the more greedy, the bigger of a bully this atom is. So the really greedy atoms we're going to deal with are oxygen and nitrogen. So I think of oxygen and nitrogen as kind of the bullies. They really want those electrons closer to them, okay? So even though, like you see here, okay, where there's carbon, okay, so I'm telling you in here, it's carbon and 4 hydrogens, they all get along, right? Because carbon is not greedy. He will gladly share his electrons equally, okay? So again, very neutral. But down here, when we're looking at water, oxygen's a big old bully, okay? He's much larger than hydrogen, and he says, I'm going to share these electrons, but I'm going to pull them closer to me. And so in doing so, because electrons have a negative charge, because oxygen pulls them closer to him, he's going to have what we call a partially negative charge, okay? So when we have oxygen, there's the oxygen, and here's our two hydrogens, okay? So again, hydrogen is donating 1 electron, oxygen is donating 1, okay? Because remember, it already had 6 total. So I'm only drawing that valence shell, okay? So they're happy, but oxygen, being a bully, is pulling those electrons closer to it. So it has what we call a partially negative charge, because electrons are negative. So if those electrons that are negatively charged are closer to oxygen, he's going to be a little more negative than the hydrogens. So because the electrons are farther away from those little hydrogens, they have a partially positive charge, okay? So we need to give some sciencey terms to that, okay? Those carbon-hydrogen bonds, again, carbon is not greedy, okay? So he is sharing those electrons equally. There are no partial charges. So we call this a nonpolar covalent bond, equal sharing of electrons, no partial charges, okay? But oxygen, same thing with nitrogen, because they're greedy and they pull those electrons closer to them, they have that negative, partially negative charge, whereas the hydrogens will have that partially positive charge. We call this unequal sharing of electrons, okay? And that's what forms a polar covalent bond, okay? So one more time, covalent means that these atoms are sharing a pair of electrons. Polar versus nonpolar just tells you, are those atoms sharing those electrons equally or not? Equal sharing of electrons is nonpolar, and there's no partial charges. Whereas if there's a greedy atom involved, there's unequal sharing of electrons, and there are partial charges. So why do we care? Well, here's that water molecule, okay? Again, greedy oxygen has partial negatives, and the small wimpy hydrogens have a partial positive. Well, what do we know about things with opposite charges? They attract, right? So this partially positive hydrogen is going to form a very weak hydrogen bond between a partially negative neighboring oxygen, okay? So here's what I need you to write down, okay, and highlight it, star it, whatever. Hydrogen bonds form between molecules, okay? I'm going to repeat that. Hydrogen bonds form between molecules. This water molecule right here, it's made up of polar covalent bonds. This other water molecule, it's being held together by polar covalent bonds. Covalent bonds are as strong as it gets, okay? But because they're polar covalent bonds and they give these partial charges, it allows this weak attraction or hydrogen bond to form between a partially positive hydrogen, hence the name hydrogen bond. It's always between a partially positive hydrogen and a partially negative atom. Again, for us, that will normally be an oxygen or a nitrogen, okay? So on an individual level, very weak bond. But when you have an ocean full of them or a water bottle full of them, then there's strength in numbers. All right, the last type of bonds that we're going to talk about is medium in strength. So covalent is the strongest, ionic is in the middle, hydrogen is the weakest. We're going to look at salt. Table salt is sodium chloride, so NaCl. Well, how do we get this? Well, first we need to look at sodium by itself and chlorine by itself. If you draw the electron distribution diagram for sodium, it has 11 protons. So 2 in the first shell, 8 in the second shell, but only 1 in that last shell. Well, remember, how many does that last shell want? 7. So it's really unhappy because it only has 1 out of the 8 possible electrons. Well, let's look at chlorine. It's got 17 protons, 2 in the first shell, 8 in the second shell, 7 in that last shell. So chlorine is really close to being happy. He's only missing 1 little electron. So sharing here isn't going to work. right? Because even though chlorine only needs 1, sodium needs 7. Well, chlorine doesn't have 7 to give. So what ends up happening is chlorine is just going to take this electron away from sodium. Okay? Sounds mean, but it's not, because look at what happens. When sodium loses its only electron in this third shell, it loses that shell entirely, but that means it's left with a happy, full valence shell. Well, what happens when chlorine steals that electron? Well, now it has 18, so its valence shell is full. So both of these atoms are now happy. But because chlorine stole a negatively charged electron, it has an overall negative charge. Whereas sodium, it lost that electron, so it is overall positively charged. And as we know, opposites attract. So there's a much stronger bond here between a positively charged atom and a negatively charged atom. All right, so this is what you really need to understand, okay? Please note just the basic gist of what's going on for each type of bond, and think about what that means in terms of their greediness or their electronegativities. With carbon and hydrogen, so that's something you're definitely going to want to write down here next to the nonpolar covalent bonds. That's going to be our carbon and hydrogen bonds. Carbon and hydrogen have similar electronegativities. Nobody is more greedy than the other one, so they equally share their electrons. If there's some differences in their electronegativities, like oxygen and nitrogen, which are greedy, they're normally going to form polar covalent bonds. But if there's really, really, really different electronegativities, like we saw with sodium and chlorine, then it's just easier to straight up steal or lose an electron. And that's when ionic bonds are formed. So please highlight this, rewrite it, box it. You're going to want to keep this in mind. All right, that's the end of this video.